2 of this section is, again, converting between rectangular and parametric form. So, given a rectangular or Cartesian equation, we may want to create a corresponding set of parametric equations. And there's infinitely many ways you can parameterize an equation. All right? For example, here, the simplest case, let me write down what the simplest case is, or simplest way. Give the independent variable the parameter t. All right? So that's like the easiest case, the easiest way to go about it. Of course, I mean, it doesn't have to be t all the time, you know? So, for example, let's look at example number 6. Well, write a set of parametric equations for the rectangular equation y equals 2 over x minus 1. Well, in this case, it's important to determine what independent variable is and what the dependent variable is. And in this case, we can tell that the independent variable is x. So that's the variable for which we're going to let the parameter t. So when we write the set of parametric equations, well, that's x equals to t, and y equals, just replace t, whatever you see the letter x in your function, which is 1 over t minus 1. So that's one example. And yes, even though they were asking one set over here, I'm going to do a few examples just so you can see how this works, of course. I mean, and also, again, these parametric equations describe the path. Yes?
2 over 2 minus 1?
Yes, 2. Thank you. So this describes the path over a particle is traveling. You know, it could be a car, an airplane, or, you know, in the video game design, you know, so when these computer engineers working in the gaming industry, they are designing mechanics for like shooting games. You know, they want to have any bullet or any rocket follow certain path, and getting as far as somewhere or following certain speed, etc. Well, that depends on the choice of the parametric equations governing that path. For example, well, this is one of the easiest ways. Another way to do this is, well, you can do x equals to t plus 1. That's another way to parameterize, and that's going to be 2 over t plus 1 minus 1. Well, that's 2 over t. That's another way. All right? There's another way to do this. How about x equals e to the t? You want to make it exponential? Well, why not? So y will be 2 over e to the t minus 1. And even better, I don't know, you want to make this x equals the square root of t. And, well, so y would be 2 over the square root of t minus 1. Well, I mean, we can parameterize these equations in an infinitely many ways. However, what are the differences when we are choosing, for example, the radical function versus the exponential functions, or with just t in this case? Well, so that depends on the purpose of our design of these parametric equations. For example, if you want to work with times that are only 0 or greater, well, maybe you want to design your parametric equations with a function that meets those domain conditions. You want to make sure your domain doesn't include the t equal to 0. Well, use e to the t, because e to the t is never 0. So we're going to look at more details about this in the last example, by the way. In the meantime, well, all we're doing here is coming up with different ways to parameterize the same rectangular equation, or function, right? Well, it's an equation, yes. Let's do another example. Write a set of parametric equations for the vertical line x equals to 4. All right, that could be a little tricky. How about we draw the vertical line x equals to 4, and well, so that's our vertical line. And well, I mean, even though it's kind of tricky, there's already a freebie here. I mean, x equals to 4. So x equals to 4. And y, what's y in this case? In this case, well, y can be anything. And again, is your favorite number? How about just t, you know? So plug in x equals to 4, and your y value can be anything. I mean, 1, 2, 3, 4, 5, and that point will still be on the vertical line. Even if you do another parameterization, for example, x equals to 4, y equals maybe t squared, for example. Even if you do your favorite point, your favorite value of t, for t equals to 1, t equals to 4, t equals to -5, you will still have the same x equals to 4, and those points will still be on the vertical line. Again, there is not a unique way to parameterize this equation. So this is one way, this is another way, even cubed, even a radical, again, your favorite number or your favorite function. All right, so let's see what's next. Okay. So let's keep going with parameterizing equations of lines. Well, so we're going to find a set of parametric equations for the line that passes through the points 1, 5 and 3, 2. Well, the exercises that we're going to do next, at least the next 2 or the next 3, it's basically a preparation for what you're going to be doing next semester in calculus for those of you who are going to take it. Well, number 1, let's, for example, number 8, we're going to parameterize it the traditional way, which is finding the equation of the line, connecting the 2 points, and then give the easiest parameterization possible, which is t on the independent variable. So number 1, how about we find the slope? So m, which is y2 minus y1, that is 2 minus 5. Over 3 minus 1, that's the differences between the y's over the difference between the x's. So that's a negative 3 over 2, and this is -3/2. So now that we have the slope, we can use the value of the slope and any of the points with I'm going to use the first point, the initial point. And that's mx minus x1, and this will be y minus 5 equals m, which is -3/2, x minus x1, which is -1 in this case. Well, x minus 1 rather. Well, so I'm going to distribute this y, well actually, yes, -3/2, x minus, that's a +3/2, and minus 5, that adds up to 5. And combining these two numbers together, 3/2 plus 5, that should give us, well, y equals to -3/2, x plus 13/2. So that's what we usually do to get the equation of the line using the point-slope form. So we have a point, we found the slope given the 2 points. So now we're going to come up with a parametric equation set. So, well, again, the easiest way to parameterize any function is give the letter, the independent variable, in this case is x, give that your letter t. And just replace whatever you see the t, y equals to -3/2 of t plus 13/2. And that's how we parameterize it. Well, so that's one way to parameterize equations of lines. However, in Calc 3, you will use a different method. Well, I really don't want to get into the details because, well, Well, just roughly speaking, so at the beginning of the semester in Calculus 3, you're going to learn about vectors and how do you find a vector given 2 points, finding that vector is defined by the terminal point, by subtracting the values of the terminal point minus the initial point. And well, and you will learn as well that in Calculus 3, the parametric equation in 2D or even in 3D, there's really no slope like a rise over run the way we have it in functions of rectangular functions. In parametric functions, it's a little different. So some sort of a shortcut, not necessarily a shortcut. So hold on, it's freezing. Okay, so a quick way to parameterize a function, or a line given 2 points, all you have to do is subtract, for the x equation, subtract x2 minus x1, multiply that by t, plus the initial x, and for the y equation, subtract y2 minus y1, multiply by t, and that's that adds the initial value for y. So for now, just try to memorize this formula for now. Again, this is going to make a lot more sense when you get to Calculus 3, because these differences between the x's and the y's are really the difference that we perform in order to find the vector that relates the distance between those 2 points. And in this case, well, in parametric equation, a straight line, there's really no slope about this straight line. In this case, it's a line that goes in the direction of a vector instead of having some sort of rise over run, which is what we're used to. But again, that's Calc 3. All right. Well, I don't know what's going on here. My computer is freezing here. Okay. Hold on. Okay, so let's write a set of parametric equations for the line that passes through the point -8, 1 and 10, -5. So let's label these values right here. Let me label this as our x1, y1, x2, y2. So all you have to do in this case is x equals to x2 minus x1, t plus x1, y equals to y2 minus y1, t plus y1, and just plug in the values. So that's going to be x equals x2 minus x1, that is 10 minus -8, careful with the subtraction here, t, and plus x1, which is -8, and for the y equation, that's going to be -5 minus 1, and t times t plus the initial value of y, which in this case is 1. All right. So just simplify this calculation and you get your parametric equation. So no need to find the slope. We use the slope form to actually come up with the equation. Just do this operation. And again, you're going to do a lot more of this when you get to Calc 3. So that's x equals to 10 plus 8, that's 18. 18t minus 8. And y equals to -6t plus 1, and that's our set of parametric equations. All right. Yes, it looks a little different. This equation looks a little different because we don't have just the t for the independent variable as we did before. So we have something other than just t. So okay, let me see what's going on here. All right. Okay, one more example. Well, for the next example, we have we have a parabola here that is y equals x squared plus 3 and t equals to 2. Well, so in this case, they're not just asking us to come up with a set of parametric equations. In fact, they're asking for a very specific set of parametric equations, a specific set that satisfies the following conditions. The condition that when t equals to 2, and the particle traveling along that parabola is at the point 1, 4. Well, so number one, let's try the traditional way. So for the traditional way is to give the independent variable, which in this case is t, y equals to t squared plus 3. So that'll be, again, the easiest way to parameterize the equation. And I mean, we got it, right? However, let's see, does that set of parametric equations satisfy the condition that when t equals to 2, we get the point equals 1, 4? Well, let's find out. Plug in t equals to 4, so that's x equals to, t equals to 2. So that's going to be 2, and y equals to 2 squared, which is 4 plus 3. So we get the point 2, 7. So that's not the point 1, 4. So we need to make a modification in order to make the point, or to get the point 1, 4 whenever t equals to 2. So, well, number one, don't erase this. Actually, just cross it, just so you can see, so you can keep it in your records about why it's not going to work, why is this really not the final answer. And well, okay. We need to modify this set of parametric equations in a way that it actually works. So x and y, well, how do we get the value of x equals to 1? Well, if we plug in t equals to 2 over t, well, that's going to give us the x value of t. How do we make that to a 1? Divide by 2, that's one way to divide by 2. I didn't think of that one actually. I was thinking of something else. So divide by 2 and then t over 2 squared plus 3. Okay, let's see if it works now. So t equals to 2. So, okay, t over 2, so that's going to be 2 over 2, which is 1. And over here, 2 over 2, it's 1 squared. And oh, not t, it's actually x. And y equals to, it's 4. Actually, it works. This parameterization works. However, I was thinking of something else, so the other possibility I was thinking is x equals to y equals to t minus 1. And then t minus 1, quantity squared plus 3. That's the other possibility I was thinking of. Either way works to satisfy the condition in this case. All right. And well, let's look at one more example to wrap up the section. Well, so what do we have over here? We have 4 sets of parametric equations, and that's going to give us the position of a moving particle at time t. Each set gives the same function when eliminating the parameter. So what we're going to do here is describe the differences. All right. So number one, this is what we're going to do. I'm going to graph these functions actually. I'm going to go to my graphing calculator, following that. Well, anyway. So we got this graph from the graphing calculator, which I didn't film, but I'm going to film the remaining ones. So we get this. We get the equation for letter A. Let's label letter A. And it's the graph of we'll see what it is. We'll see what it is. And in this case, it's important to show arrows to denote the direction at which it's going. Well, so to eliminate the parameter, in order to eliminate the parameter, go with the easiest of the equations in your set of parametric equations and solve for the letter t. Well, in this case, the easiest equation is y equals to t. All right, the easiest equation is y equals to t, and well, it is already solved for t. I mean, we can just reverse the equation to say t equals to y. All right, so in this case, so if well, let me call it y equals to t, x equals t cubed, but in this case we're saying that t equals to y, so we're going to replace this with a y. X equals to y cubed, and well, to solve for y, to get y as a function of x, we can take the cube root on both sides, and y equals to the cube root of x. And in this case, let's point what the domain is. Well, I mean, we can see from the graph that the domain is the set of all real numbers, and we're also obtaining a function here for which is the cube root of x, whose domain is the set of all real numbers, that is negative infinity to positive infinity. All right. Let's look at the second example and see at part B, right here, and see what's going to happen in that situation. Well, so it's essentially the same set of equations. However, both equations have a negative sign in front of it. So let's graph them. And well, let me say I can insert negative. So I can insert negative and see what happens. And check this out. This one this time is going to go backwards this time, right? So direction matters. Well, so I'm going to do this instead. But well, how do you guys are going to know that I draw it from right to left? I mean, you saw it live, but I mean, if you're seeing the paper, well, that's not clear. So again, put some arrows to denote its direction. And well, again, let's eliminate the parameter. So well, the domain of the function is indeed, I mean, by looking at the graph, it's a set of all real numbers. Let's eliminate the parameter. So in this case, if y equals to negative t, this implies that t equals to negative y. And in this case, we know that x equals to negative t, or negative t cubed rather. So I'm going to replace x, or rather the t, with negative y. And be careful here, because a negative quantity cubed is going to remain negative times the negative in front of it. X equals y cubed, and solving for y equals the cube root of x. And again, it's going to have the same domain, negative infinity to positive infinity. All right. So essentially, for the first couple of cases, A and B is the same equation, different signs. That means different directions. There's nothing weird about it. However, let's have a look at letter C. For letter C, that's going to be an interesting one. So what do we have? X equals to t to the 3/2, and y equals to the square root of t. So I'm going to go to my graphing calculator, and I'm going to type these equations. So let me clear all this. And okay, clear. And well, on the one hand, what do we have? T raised to the 3/2. And for y, what do we have? The square root of t. Okay, again, check what's going to happen this time. We only have one of the tails of the cubic graph, because well, they're already telling us that each function gives the same, when eliminating the parameter, gives the same function. However, the graphs based on the way that they were parameterized, they're not giving us the same graph. All right, in this case, they're only giving us a graph whose domain is no longer the set of all real numbers. In this case, it's only from 0 to infinity. And well, if you're wondering why is that, it's because, well, check the equation for y equals the square root of t. What's the domain of the function y equals square root of t, or square root of x, doesn't matter. Isn't it only the set of all positive numbers and 0? That explains why we are only getting the positive counterpart of the tail. In this case, well, So, and let me be clear about something. I'm going to draw a full bubble here. Whoops. That's not what I wanted to do. I wanted to do this. All right, and in this case, it's going in this direction. And let's eliminate the parameter. All right, so let's go with the easiest equation. To me, the easiest equation is the second one, the one with the radical, because the first one has rational exponent. I don't like them that much. So y equals to the square root of t, and I would like to square both sides to get t equals to y squared. And then I'm going to substitute this back in the original, or in the other equation, the x equation, that is, okay, first of all, t equals to 3/2, where in this case, this is t equals to y squared. And well, what's going to happen when we have the power of another power? In other words, multiply the powers. However, when we multiply 3/2 times 2, check how these two are going to get canceled. That's going to leave us with y cubed. All right? Isn't it the same function we've been getting all the time? X equals y cubed, which is the same as saying y equals to the cube root of x. However, in this case, we need to be very specific, because even though, yes, we're getting y equals x, y equals a cube root of x, y equals a cube root of x, y equals a cube root of x, this third case scenario, it's not containing the same domain as the previous cases. In this case, the domain is 0 to infinity. All right? Let me see if I can make some more space here. All right. Yes. Let's do the fourth case, the last case. E to the negative 3t, e to the negative t. Well, the parametric equations here look totally different than what we have in the previous case. I mean, we have other transcendental functions, no longer polynomial functions or radical functions like in the third case. So let's see what's going to happen this time. So let me clear all this. And so in this case here, second e to the negative 3t, and oops, I don't need to close parentheses, and e to the negative t, and check what's going to happen this time. All right. Well, number one, this time it went in the reverse direction, isn't it? However, okay, here is the thing right here. So even though it's going in this direction, the problem with graphing calculators, so that's why I wouldn't rely on a graphing calculator 100%. Yes, graphing calculators are very smart devices, however, they're not that smart. So here is where we need to understand the properties of certain particular functions, in this case, the exponential function. So can e to the t, or e to the negative t, whatever, can it go to 0 at one point? Never goes to 0. I mean, try it algebraically. You know, take ln on both sides. Okay, cancel ln with t. Negative t equals to ln of 0, which in this case is negative t, equals to undefined. All right? Or I mean, careful, because we're not finding a limit. The limit is negative infinity, but we are evaluating the function. The function is undefined in this situation. So how do we represent this undefined thing? Well, I mean, we need to represent this with an open circle in this case. So that means the particle, the rocket, whatever it is, a bullet or a plane or a car, yes, it's going to travel in this direction, but it's never going to touch the origin in this case. So now let's work on eliminating the parameter. Well, So from the set of parametric equations, well, there's a couple of ways to eliminate the parameter. One takes longer, but I'm going to do the shorter way. One way, well, let me describe the long way real quick. The long way is to go to the second equation, which I believe is the easiest one because it has less coefficients. Solve for t, but that'll take two steps. Number one, take the ln on both sides to eliminate the e, and divide both sides by -1 to get the t by itself, and then plug that in back in this first equation. So this time I'm just going to use, check this out, I'm just going to use y equals to e to the -t, and I'm going to name here x equals e to the -3t, which in this case is the same as saying e to the -t quantity to the third power. All right, so I am multiplying the powers, you know, so power of another power multiply the powers, but in this case I'm doing this backwards. So, well, we know in this case that e to the -t equals to y, so I'm going to replace that over here, and that's going to give us x equals to y to the third power, which is x equals y cubed. And in this case, simply y equals to the cube root of x, which is again the same original function, isn't it? Which is what they were telling us here, that every set we have above gives back the same function when eliminating the parameter. However, there's main differences based on the design of these parametric equations. The first way designs the function to have a particle traveling from from west to east. The second case designs the pattern to go from east to west, and the third variable, the third set of equations describes the particle to travel from west, towards the east, however, starting at the origin, not coming from the west actually. And the last case scenario, well, it's coming from the east and it's sort of trying to get to the origin, but because of this restriction of the exponential function, it's never going to touch that origin. And again, this is what your graphing calculator doesn't show you. Graphing calculators are not that smart to show you these removable discontinuities or holes, or the gaps are kind of shown, but what they also don't show you are the asymptotes. So that's where in this case we need to understand everything about asymptotes and holes and all kinds of discontinuities, because our graphing calculator doesn't do a good job about it. All right, and in this case, well, one more thing is to actually state the domain. And in this case, the domain of this function is from 0 to infinity. However, as opposed to the previous example where the 0 is inclusive, in this last case is exclusive. All right? So careful on how do you parameterize equation. Need to care about the domain of the n, in this case, of the end purpose in this case. All right?